Perfect. Good morning, good afternoon, good evening, and thanks for joining this instance of the Antrea community meeting. Depending on where you are in the world, it's either the 30th of January or the 31st of January. And for today, we have a presentation related to TIA project. More specifically, we have Tushar presenting a throughput anomaly detector for TIA. And yeah, so this will be a presentation that involves the implementation of this detector in the TIA solution with the ClickHouse backend. So, and well, I probably better stop talking now and let Tushar do all the talking. So Tushar, please go ahead with your presentation.
Thank you, Salvatore. Good morning, everybody. Good afternoon and good evening for all the folks over here. So I'm going to present the TIA throughput anomaly detection. Let me share my screen with you guys. Let me know if you can see the screen. Can everybody see the screen?
Yes.
Yes, we can.
Okay, all right. So basically, TIA throughput anomaly detection is, as the name suggests, it's an anomaly detection technique. So it is kind of like you are detecting any abnormalities in the network. So this is one of the features that we have implemented as part of network traffic analysis in TIA. So the thing is like, so basically, if you understand this thing, like why there is anomalies in the network, that could either be because of some minute simple reasons, or it could either be because of a threat in the network. So it is always better to have that analysis, to have that things told to us beforehand, or at least we should be able to analyze that there is an anomaly, there is something going on wrong in the network. So this is where the throughput anomaly detection comes into picture. So we have used like three algorithms for this thing. The first one being EWMA, so the exponentially weighted moving average. So it is basically used in the time series analysis, and this model is used for in order to figure out the throughput difference. So basically, there's a difference if there is a difference between the forecasted throughput and the actual throughput, and the difference is too big, we'll be saying that there is an anomaly in that thing. So how do we detect that? This algorithm uses weighted points in order to figure out whether the analyzed throughput or the calculated throughput, in order to find the calculated throughput. So what it does, it gives higher weights towards the newer points and the low weights towards the older points, and that way it is able to figure out, like there's a whole complete derivations in this equation in this, which we will not go through because that will be too much. So for now, it is basically just understand it like this, that you have some throughput that should be there, and then there's a calculated throughput, and if the difference is too much, that is where you find an anomaly. And the second one is ARIMA. So I call it ARIMA. I'm not sure if it is ARIMA. Sorry if I'm pronouncing it wrong. Autoregressive integrated moving average model. So basically, it is also the subset of linear regression. So basically what it will do is like it will figure out a linear pattern in the model where you find the throughputs, and then if there is a throughput which is way far than the linear regression model, then we can say that, yeah, there was an anomaly in that, because it shouldn't have happened like this thing, right? So that is ARIMA model for you. And then there is DV-scan model. So DV-scan model is basically like when you do the density-based spatial clustering of application with noise. So what it means is like, let's say that you have some throughput values that is making a higher density point in one area, and then there could be multiple clusters of density points in any network. And if you find any point or a bunch of points that are like far away from these things, from these clusters, then you can obviously say that, yeah, there is an anomaly. So that is like the big picture over here in this. Now, if we go into how did we implemented throughput anomaly detection and what actually happens in the backend. So what we actually do is like we have created one CRD, so a custom resource definition in Arthia software. So what that does is it allows so custom resource definitions basically allows you to have a custom resource deployed on your cluster. So let's say that I have made a custom resource of for example, throughput anomaly detection Spark job. So you can have a pod that will run specifically throughput anomaly detection Spark jobs. If you want a different custom resource, you can do that as well. And this is basically the CRDs are basically to for you to use any custom resource that you want to use in the cluster. So what happens once you have created the cluster and now what you have done is like you have started an instance of that custom resource. So once you have, you give the Kubernetes that there is a definition. And if there is a resource that obeys this definition, please help me out and give that definition the name of the name and resource of the custom resource definition. I'm sorry, I'm using so many words over here, but basically it is like that. So, what once that CRD is deployed in the Kubernetes, and then you try to include new object as a custom resource in this, what you will do, you can either do it through YAML files or you can use our Thea CLI. For this demo, we are going to use the Thea CLI, but you can obviously use YAML files as well. And then you can also like curl to that base API. So basically, yeah, whenever you create a custom resource custom resource definition, you also create a base API, and all the resources based on that custom resource definition are going to be under the base APIs. And then it could be different things like you can do views, you can do lists, you can do stats, you can do status, and a lot of things in that specific API. So after you have created a CRD, yeah, and then you create a new job. So what happens when you create a new job? The TS CLI is going to, so the place where you use the CLI, that is Thea Manager. Then this Thea Manager is going to include that Thea CLI and is going to send it to a controller. So the controller that is going to be responsible here will be the TAD controller, throughput anomaly detection controller. Now this controller is going to utilize all the arguments that we have passed to the Thea Manager, and it's going to make a specific command that will help us invoke a Spark job. Now, how will a Spark job be invoked? And that happens because after the controller, it goes to a Spark operator. A Spark operator is basically a place where you have already made sure that your images of the new job should be present. So the Spark operator will take this CRD and will create a new instance. For example, at our stage, we'll have the TAD instance. And what I mean by TAD instance is having a driver Spark driver pod. That Spark driver pod is then going to create the executor pods. Now, executor pods are basically responsible for any action that you do in your specific application. So we have a TAD application that is going to do some things in the backend, and these things are going to happen in the Spark executor pod. And now the things that are going to happen in the backend are basically the Spark executor is going to run the script. The script is going to take all the arguments that we have passed to it. It will go and analyze the data that is already present in the ClickHouse table from in our Kubernetes cluster. And from this ClickHouse data, it will take all the flows table. Now the flows table has the data of source IPs, source port, destination IPs, destination ports, what protocol we are using, and the throughputs that we have seen till now. So that they are the actual throughputs that we have seen. So it is going to contain all those data. Now that data will be passed to a specific algorithm, the algorithm that you can choose as a user And that algorithm will go and calculate all the throughputs that should have been there. And based on the throughputs that have been calculated and the ones that were already present, we are going to see if there is any difference. If the difference is too high, then we can say that, yeah, there is an anomaly. If the difference is not too much, then we can say, yeah, it's just like it's simple calculation thing. So we'll just go ahead with it. So it is not an anomaly actually. So I know like this is a lot of thing that I just threw I just threw on you. So to see it in action and to understand it more, let's move towards the demo part of it. So as I was saying, there should be a CRD, there should be a custom resource definition, and this is the custom resource definition. And there would be throughput anomaly detectors, the name of the resource that we are going to pass, and then there will be the APIs is going to be stored in the CRD Thea Antrea.io. The as we know that there's always like some things that are required in any new resource. For us, the only required resource is the spec, and the spec will have only one required resource, and that is the job type. Now, what is the job type? We'll go and talk about this later. For now, it is like there will be a job type. There could be a start interval, end interval. There could be instances. There could be driver core request and everything. And just to give you a little brief on this thing. So these last 5 things, the executor instances, driver core request, driver memory, executor core request, executor memory, these all are basically the arguments that you send to a Spark job. So as your Spark can reserve specific memory, specific cores for you as a driver, as well as for the executor pod. So these are basically for that Spark. The end interval is start interval is basically like from where till where you want to see if there is any anomaly. And then job type, basically it means like which algorithm you are going to use. So it could be the ARIMA, it could either be AWMA, or it could either be DBScan. So as we can see that we currently have like 5 pods running in our flow visibility namespace. And what we can do is we'll go to the Thea manager. So Thea CLI, sorry, Thea CLI. Thea CLI is basically it is like normal CLIs that we see everywhere. So it has different commands that you can use: the ClickHouse, completion, help, policy recommendations, or a support bundle, throughput anomaly detection. And the one that we are interested is in this. So let's go inside this. Let's say it's throughput anomaly detection. And let's go into the help of that. So as we go inside the help, it says like there should be a command that should be EWMA, ARIMA, or DBScan. And also it says alias, as it could be either throughput anomaly detection or it could be TAD. So as you just saw me like writing a whole thing, instead of this, we can just write TAD, like Thea TAD help. So that also works. Now the commands that are available with us is delete, list, retrieve, run, and status. The one that we want to do right now is run. So let's try to, we'll get back to all the other commands as well. But for now, we are going to use the run command. So let's say Thea that run, and let's go into the help of that. So as we go into the help of Thea run, as you see, we have different things as we saw in the CRDs: driver core request, driver memory, end time, executor core request, executor instances, executor memory, start time, and then the type of the string is basically the type of the algorithm that you are going to use. So for this demo, we are going to use that run, and let's take the type as ARIMA, and let's give it the driver memory as 1 GB. So basically this is the command that you have to pass from the CLI part of it. So once you do that, you see successfully started throughput anomaly detection job with name ARIMA. So let's see which instance it has created. As we can see, see over here we have a new Spark driver that has started running. So let's try and check its status. So first, to check the status, we need to know what is the ID that it has. Like we can obviously fetch ID from here, but let's see if we can have it from our list as well. So Thea add list, and if we say, so it says like there is a name that is this, and then there is a status that is running, right? So now I understand like this could be an ID, but do not get confused due to name in this. I'll show you why I'm saying this as name. Let me actually show it quickly to you guys, like why I'm saying this as a name. So as you remember, I told you there will be a base API. So currently we have the base API under the anomaly detector Thea Antrea OIO with the resource name as throughput anomaly detector. So let's try and get this. I guess I do not have the token here. Okay, we'll get back to that thing later. Let's try to do it over here because the executor port is started running. So the driver has already included an executor port, and the executor port is running right now, and it is doing its things. Let's see what is the status of this job. So to do that, we have status. Like I can show you help as well. So it says like in help, you can just show the name. So name is basically like you can either just write the ID of that. So for that reason, let's first try the list, and the list we are going to do the status. Status will be of this specific ID. And if we go into this, so it says like 50% has been completed. So there's like this status is going on in this thing. So yeah, currently it is running. It is showing all the status that it has completed right now. Stage is all that it has completed. It should take around 2 minutes for that time. And as I told you that as I told you in this slide that once the executor pod has executed all the function or has done everything, it is going to update. It is going to populate a table inside the ClickHouse database. The table name will be TA detector. So we can, on the side, we can go towards our ClickHouse. And once we are inside ClickHouse, let's see if it has the tables. And we can see there is a TA detector and TA detector local. Just to avoid any confusion, these tables are made as a part of ClickHouse deployment, and it is not responsible because of the CRD that you create. So there could be multiple other tables that has nothing to do with the CRD and still be present inside the ClickHouse database. So as we see, the driver is also completed. Let's see the stage. Stage says like the status of this anomaly detection job is completed. So, okay. So let's see what it has done. So let's go select all from, and the table name is TA detector. And we can see it has created 21 rows in that. And now just to show you guys, like I'll show you what is this data and everything in a better way. But just to show you how many actual flows were present in which we have seen the anomalies in 21 rows. So select all from flows. That is the input table that we use currently. So as you can see, there are 3,000 rows in this, and we have only stored the data for the in which there is an anomaly. So we are not going to use the whole data store. We are not going to duplicate the storage in this, so as like just to keep the memory short. So we are only going to use we just use the places where there is an anomaly. And now to see it in a better shape, let's see Thea TAD. And let's go back to the help thing. So we have already seen list, we have already seen status. Now we'll do the retrieve. So retrieve is basically like having a result of what you have done. So instead of status, I'll just write retrieve over here. So let's say retrieve, and then I can like, because this could be big data, like bigger data, not like big data thing, like bigger data. So I'll just write it into a file. So let's say output.json file. And let's see if we have the output.json file. So you can see like this is the ID. This is the ID that we were using right now. This is the source IP. This is the source port, the destination IP, destination port, and the place where when we saw this anomaly is this. We calculated the throughput, which was a little different with what we saw. And there's like throughput found in like two of such flows from this port. So that is one. And then you can see the next ones, and these would be specifically like if I have to guess, actually not guess, but actually the truth is like these are going to be 21 tier 21 data. We are working on whether to write this data as JSON or whether we want to put it as a table. So just to make it easier for the user to go through this table and figure out what is going on. So this is basically the thing. And to show that, let me try to get the command. If I'm not wrong, I just missed the token. So let me try to find the token for now. Okay. Yes, and the token. And if I do the call now, say, yeah. So we can see this CRD has been registered, and we can see the ID is over here. So the reason why we use it as a name is because in the metadata we have created it as a name. So that's why we keep it as a name over here. So that is pretty much it. And the only command that is left is now the delete one. So I can show you guys like Thea, dad, delete, and the same thing, just keep this ID, and it has been deleted. Now if we see inside, let's go and try in the detector. So the table has been cleared. If there would have been any driver execute a pod running, that is also cleared. And now let's try and fetch this data again. And as we can see that there is a kind, but there is no metadata, there's no items that are present because there's no other throughput anomaly detection job going on. Just to verify that completely, let's do the throughput anomaly detection list, and you can see there's nothing inside this. So this is basically throughput anomaly detection. Now, what do we do actually with this data is over here. So as you can see, we have calculated the present throughput, the one that we already had, and then the calculated EWMA throughput and the ARIMA throughput. So we see there are multiple spikes in this data, in this table. When we visualize the table that we just got from the flows and the ones that we calculated after doing the Spark job, this data shows us that there are multiple spikes, 1, 2, 3, 4, 5, 6 in particular. But we can see that the ARIMA or the EWMA reaches the first spikes. Like they're quite close, they're not that far away. However, when we move towards the end and the two spikes, they are quite far. So that is where we see we say that yeah, there is an anomaly. So not every spike could be an anomaly, but yeah, some spikes could be an anomaly. And this thing is what we are calculating. We are figuring out whether it is an anomaly or not. So this is basically the presentation. I've taken the references from Yongming's radio table or radio paper, and also from Subramanian's internship project. So that is pretty much from my side. Thank you. Let me know if you guys have any questions.
Thanks, Tushar. That was a nice demo. And let's open it up for questions. So if you have any question, any suggestion, observation, anything you'd like to ask Tushar, please go ahead.
So actually, so this anomaly detection is for like, what is the purpose of it? Like, I mean, it is like works across a single cluster, or like it can work across multiple cluster. And yeah, so.
Yeah, so basically the purpose of having the throughput anomaly detection is just to figure out if there is an anomaly. It could, as I said, like it could be either because of some threat, or it could be just because something went wrong in the network or something like that. But we should be aware of that there is an anomaly going on in our network, and based on those anomalies we can figure out if it is a threat. So it is basically a part of network traffic analysis.
So Rajnish,
Okay.
to add to your question is operates on the data that are stored in the TIA flow database. And at the moment, these are the data which are sent from the Antrea flow aggregator, which pertain only a single cluster. So we don't have, we don't run the analysis across data for multiple clusters yet.
Okay, so basically it is on the data which is on which it is analyzed, like.
That's right. That's right. If you had the data pertaining network flows for multiple clusters, then it would also identify throughput anomalies in traffic across multiple clusters. Because at the end of the day, the throughput anomaly detector is an algorithm that analyzes data in a network flow, and it doesn't care whether source and destinations are in the same cluster or not.
Okay. So so it is also like a DB based data, or like it's just a network flow? I mean,
the network flows are stored in the ClickHouse
Yeah.
database that Tushar was mentioning. Basically, this is part of the generic T architecture where you have, as you know, in the Antrea agent, we have the flow exporter that captures network flows and sends them to a centralized aggregator. The aggregator does correlation between flows to match sources and destination, and then sends them either to ClickHouse for the in-house installation, or to Snowflake when people are using Snowflake as a backend. And yeah, and then that's once the data are in the ClickHouse database, this Spark job analyzes the data in the database. That's so let's say that the part about running the algorithm and analyzing the data is sort of a different pipeline from supplying the data in the database.
Okay, thanks.
Okay, good. Yeah, please, any more question?
Is this possible to have it run in the background instead of like triggering jobs manually?
So currently we are using it manually, but we are working on the one that can go in the background as well.
Okay, and something else you may have mentioned, maybe I didn't catch it. What data did you use for your testing? What you're showing in the graph on slide 5?
Yeah, so basically this data, as we know that our cluster is like, we do not have too much anomalies. So we just introduced, we just took the data from our cluster and then just explicitly included the anomalies in that, just to see if we are able to accurately figure out whether there was an anomaly or not. So this data is basically like input data taken from the cluster, then included with some anomalies, and then ran with the EWMA and the ARIMA algorithms.
And when you do have anomaly detection running in the background, do you expect that there could be a large volume of events? And if yes, is it something that the user can tune? Can they tune the algorithms to reduce the amount of events if they want to?
Like, I don't understand the question. So is it that if there are anomalies, then we tune the calculator to not find the anomalies?
Well, if the user thinks that too many events are generated and that the detection is too sensitive, is there a way to tweak some parameters so that fewer events are generated? Basically, something that may have been considered an anomaly before will not be considered an anomaly anymore with the new parameters, but you still have some events for the most like extreme cases.
Yeah, like I guess like Yongming would be better to answer this thing, as this thing was basically based on his paper. So I guess like basically it is like ML, so it is like training and getting the data, result data. So that could be possible, but currently we are not working on that, but Yongmin can provide better point on it.
Yeah, definitely. It's just related to arguments you pass to the algorithm. It could be triggered to a more sensitive one. But if the user find too much negative positive or too much events, we could pass some arguments through CLI to let the algorithm less sensitive, or we could set a higher threshold to generate less events. Yeah, but I think that didn't cover in this first implementation by Tushar, but we are definitely adding more arguments to a CLI later.
Okay, thanks, Yongmin. Thanks, Tushar.
Hello, just a quick question from me regarding the efficiency, okay, the effectiveness, sorry, of those algorithms. Was the minimal, is there a minimum duration of flows for each algorithm to make sure that they can make an accurate detection?
Currently, it is like, so for ARIMA, we cannot take any data if the data difference between the start and the stop is less than 3 seconds. We do not take that data.
And whereas for the others?
For the others like DB scan, so that is like cluster-based thing. So that does not include any time restriction. And I guess the same is for the EWMA. So that does not have any, but ARIMA has like 3 seconds thing. But
Okay.
that can also be tuned. We just used 3 seconds, but that can also be tuned.
Okay, understood, thanks. Yuming, sorry, were you trying to talk?
Oh, yeah.
I didn't interrupt you. Yeah, go ahead.
I just want to add at some point because Tushar means 3 seconds, and actually to more likely because of the lack of data points will cause the algorithm less accurate. For the ARMA, at least we need 3 data points for each connection. So it will depend on the interval of flow aggregator. If their interval is 60 seconds, which means that we need 3 minutes to have enough data points for each connection, right?
Mm-hmm.
So yeah, I just want to correct that. Mm-hmm.
Cool, thanks, Yuming. All right, do we have any more questions here? Please go ahead and ask your questions. I'll keep waiting for a few seconds in case you're thinking about any question here. Okay, perfect. Seems that it's all for this topic. So many thanks again to Shar for this presentation and this demo. We hope to see the code merge into the TIA source code base as soon as possible. That will be a great addition to the NTA capabilities for the TIA project. And yeah, and I think that's all on this topic. And do we have any other topic that you like to bring up for discussion today? So let's go now for open discussion. Anything that you like to discuss, please bring it up. Otherwise, it will be all for today. I'll keep waiting for a bit in case you want to propose a new topic. Well, in the meanwhile, let me also check if somebody proposes any topic on the Slack channel while I was sleeping. No? Okay. Okay, 5, 4, 3, 2, 1, and that's it. So I would like to thank, as usual, everyone for attending. Thanks again to Share for your presentation. And we will have our next meeting on February the 14th. So that's all for today. And I wish everyone a good night, a good day, or a good afternoon. Thanks for joining again, and bye.